We've solved some problems involving net force, but we haven't distinguished what made up that net force, what caused that net force, whether it was somebody pulling on it and somebody pulling on it in the opposite direction, or whether it was just one force that contributed to the net force, or whether it was 14 people pulling on it in various directions contributing to the net force. We've just assumed that we've had or been looking for the net force. Today we're going to start talking about the things that make up the net force, the forces involved in contributing to the net force. I want to define two terms here before we do that. One is weight. If people get volume and mass mixed up, then more people get mass and weight mixed up. My mass is the amount of matter that I possess, and it's measured in kilograms. Weight is not measured in kilograms. It is not the amount of matter that I possess. Rather, the weight of an object is the force of gravity acting on an object, which depends upon mass, but also depends upon the acceleration due to gravity of 9.81 meters per second squared. Mass stays the same no matter where in the universe you go. Weight doesn't. Weight changes because the acceleration due to gravity will change. Now, we can find the weight of an object simply by multiplying mass times acceleration, if the acceleration is the acceleration due to gravity. On Earth, we'd assume that's negative 9.81 meters per second squared. Although weight can be different, A can be negative 1.6 if you're looking for the weight on the moon, say. But typically, we're looking for the weight of an object on Earth, so we'd multiply mass times negative 9.81. Yeah, Ender?
Does that mean like scale that's something
Say that again?
like you're measuring the mass times?
On a scale? No, actually, that's a good question. Most scales, like bathroom scales, actually don't read mass at all. Even though it says you weigh 70 kilograms, it's not actually measuring kilograms. It uses a spring, and it kind of tries to balance that force of gravity against the spring. If you were to take that bathroom scale to the moon, it would not work. It would read 1/6 of, let's say you weighed 60 kilograms for ease of math here. It would read that you weighed 10 kilograms, but you don't. You're still 60 kilograms. That scale that you have in your bathroom is calibrated to Earth. Okay, so it actually measures weight and then just kind of converts it to mass on Earth.
So would it measure different if you're like at the top and top?
Yep, yeah, it would. Not very much different, but it would measure a little bit different if you were in Vancouver, say, versus the top of the mountain. Yes, it would measure a little bit different. Again, not dramatically. If it's showing that I weigh 70 kilograms, when I stand in the bathroom of my house, top of a mountain, it might show 69.8 or 69.9 kilograms or something like that. Not going to be dramatic, but it would be different, yeah, because it's not really measuring your mass. It's just telling you its mass. It's really measuring your weight in newtons and then just converting it to mass as per that location, as per being on the Earth. Yep.
Why do objects that 50 kilograms?
Why do objects that fall? Okay, so in the absence of air resistance, all objects will fall at negative 9.81 meters per second squared, because it's the gravitational. It's kind of hard to explain this without going a little further in physics, but we're going to talk a little bit later on about gravitational field strength in our next unit about gravitational field strength, which actually relates to Einstein talked about the curvature of space-time, which causes gravity. So the field strength relates to that. Now, Einstein's curvature of space-time is not related to what's. If you think of this as space-time, and then we put a big mass like the Earth, on the fabric of space-time, it dents the fabric of space-time to look like this. Okay, that's what causes gravity. Now, if we put something on this curvature of space-time, it's like it goes tobogganing or sledding down the curvature of space-time. And that curvature, that bending of space-time, isn't affected by what it is that's sliding on it. It's affected by what it is that causes it. It's the Earth that causes it, so its value is going to be the same regardless of whether it's a 1 kilogram object sliding down it or whether it's a 1,000 kilogram object sliding down it. Okay, that make sense?
Yeah.
Yep, go ahead.
Yep.
Yep. This curvature of space-time affects objects. Like if you have, let's say, the sun obviously dents the fabric of space-time more than the Earth does. If something happens to be flying by somewhere in our solar system, some little asteroid or something like that, it will get caught up in the curvature of space-time caused by the sun, and it'll start bending because of that. Light can do that as well, okay, although it's not quite as dramatic as an object like an asteroid, but it can do that as well. That's how actually we or scientists in the late 19-teens, somewhere around 1918, 1919, something like that, actually verified Einstein's theory of relativity. General theory of relativity was to actually observe light bending around planets or the sun or something like that. I can't remember what it was, but the bending of light. Yep.
So does that mean 9.81 meter per second squared is actually just theoretical because there's always errors?
Well, yeah. I mean, it's the acceleration of gravity caused by the Earth. But as soon as you introduce something in here like air, well, then this thing that's sliding down that fabric of space-time wouldn't necessarily slide down at 9.81 anymore. So yeah, it's a theoretical value in the absence of air resistance. Yeah.
Like in a normal space-time where you get an acceleration,
I'm sorry?
like in a normal space-time where there is no gravity, it would just be zero.
Yeah, like out here, when you're like, this is somewhere off in a distance, in a distant universe where there's no objects nearby, and space-time might be curved a little bit by distant objects, but not very much. Then we would say, yeah, there's no curvature of space-time, so there's no gravity out there.
So if you had like
Okay, quick last question, then we'll move on.
So if you had artificial gravity, like in like a dome or something,
Yeah.
would it add on to the Earth's gravity?
Well, firstly, you can't have artificial gravity, and there's nothing you can do to like flip on a switch and then artificial gravity just appears. The easiest way to make artificial gravity is actually to spin something. Okay, if you spin around, then you experience what's called the centripetal force, the force of a wall pushing you in, which makes you feel heavier. So you get artificial gravity that way. If that thing was spinning vertically like this, like a Ferris wheel, but faster than a Ferris wheel, then yeah, you could make it add on. That still doesn't change gravity, but it would change what you perceive as gravity. You feel 9.81 normally. Right now, you and I feel 9.81. But if you have something spinning vertically like that, you might feel 14. Or you might feel, depending at the top of the circle, you might feel 6 or 7 meters per second squared. Right? Because artificial gravity can affect that if it's spinning vertically. But it's not affecting real gravity, just what you perceive as gravity. Okay. Now, weight, if you look at the equation here and you look at the numbers that we plug into it, negative 9.81, weight appears to be a negative number. And strictly speaking, it is. Your weight is a negative number. My weight is 70 kilograms times negative 9.81 gives me about negative 686 newtons. My weight is negative 686. Because it's negative and it doesn't really sound right for a weight, we usually just make it a positive value. Technically, my weight is negative in newtons, but we usually just make it a positive value. Now, another term called the normal force. The normal force is what we perceive as weight. You don't actually feel your force of gravity as weight. You don't feel that at all. Let me give you an example to help you understand that. The force of gravity acting on me right now is about 686 newtons. If I jumped out of an airplane, the force of gravity acting on me is 686 newtons. But yet, I don't feel that weight when I jump out of an airplane. As I'm free falling, I feel weightless. My body feels completely weightless. The reason it feels weightless is not because my weight isn't the same. It is. My body doesn't perceive weight. My body perceives normal force. The normal force is the force of a surface acting on an object. Right now, I have a force of gravity of, call it 700 newtons pulling down on me. But if that was the only force that was acting on me, I would accelerate down into the ground at a rate of 9.81. It doesn't happen. So there must be a force pushing up on me as well. It's the force of a surface pushing up on me. It's the force of the floor pushing up on me. It's the normal force that I perceive as weight. When I jump out of the airplane, I feel weightless. My force of gravity is 700 newtons. When I stand on the ground, my force of gravity is still 700 newtons. Now I feel 700. Not because of the force of gravity, however, but because of the normal force of the ground pushing up on me. Now, this normal force, this force of the surface, always acts at 90 degrees to the surface. So, if here I am standing on the ground, gravity acting down, the normal force acts up at 90 degrees to the surface. In this case, those two forces are equal, so I would feel my normal force, but it would be the same value as gravity actually is. If I was on a ramp like this, gravity is acting down like this, but my normal force is acting at 90 degrees to the surface like this. We feel a little bit different now. You know that if you're on a slope, you feel a little bit different than if you're on the ground. If you were, let's say, on a roller coaster, on a loop, a vertical upside down loop, and you were, let's call it a stand-up roller coaster, the force of gravity is acting down, and the normal force this time, what's the force of the surface pushing on you? It's not the ground anymore, it would be the track. It's pushing down as well. So my normal force would be down. If you've ever been on a vertical loop of a roller coaster, you know that if you close your eyes, you don't know which way's up and which way's down. Doesn't matter where you are, the top of the loop or the bottom of the loop, you can't tell the difference. And that's because the track supplies not a force of gravity, but a fake force of gravity, right? Like an artificial gravity. Does that make sense? We feel the normal force. It's not gravity we feel. It's the normal force we feel as weight. Okay? Weight is gravity, but we don't feel weight. We feel normal force. Normal force and weight often end up being the same, but not always do they end up being the same. What about an elevator? You guys have all been in an elevator, maybe like a high building. Maybe, anybody ever been in the CN Tower? No? Nobody's been to the CN Tower? Used to be, until a couple of years ago, the world's tallest freestanding structure. I forget how tall it is. It's a crazy, crazy high. You get in this glass elevator, you look out over the city, going to the tallest building in the world, and you accelerate pretty quickly because you got to go pretty high. When you accelerate quickly in an elevator, what happens initially? You feel heavier. You feel heavier when you go upwards, right? You feel like your knees want to buckle. You feel heavier when you go upward, and that's because the normal force is greater than the force of gravity as you accelerate upward. Otherwise, you wouldn't go up. When you're at the top and you start going down, the normal force is less than gravity. That's why you're going downward, because gravity's bigger. Now you feel lighter as you accelerate downward. Now, it's not very long before you reach a constant speed and those forces balance again and you feel normal. But initially, you feel either heavier or lighter depending upon that normal force. Now, let's define another term. This isn't a force per se, but this is the way of putting forces together. We're going to call it a free body diagram. We're going to abbreviate it by an FBD. A free body diagram, or FBD. A free body diagram shows all of the forces that act on an object. We've already drawn a few free body diagrams. This is one. That's a free body diagram. So is this. So is this. Free body diagrams show all of the forces acting on an object. That becomes a critical tool for us to analyze multi-force problems. Problems involving not just the net force, but the forces that make up the net force. Now, I'm going to give you a method or a recipe to solve these problems that involve more than one force. Four-step method, a four-step recipe. And I'm going to ask you, please, at least in the beginning, to follow this recipe to the letter. How many people take foods class here or have taken foods class? Yeah? Remember? What did you make in foods class? Tell me something good you made in foods class. Something tasty, something yummy that you made in foods class. Jelly roll? Okay, when you made a jelly roll in foods class, you had a recipe, right? Did you follow the recipe? Ethan, you took foods class? Let's go with somebody else there. Ethan, you took foods. Tell me something good you made in foods. Cinnamon buns? Okay, did you follow the recipe to the letter? And your recipe and your cinnamon bun turned out good. It turned out the way it was supposed to, right? It turned out correct. Now, Ethan, have you made cinnamon buns since? No? Okay. So if Ethan makes cinnamon buns, the first time he makes cinnamon buns, he follows the recipe, right? If he wants to get this right, he follows the recipe. And the second time he does it, he follows the recipe. And the third time he does it, he follows the recipe. By the time he's done it 15, 20 times, maybe he can follow the recipe without thinking about it, without looking back to the recipe, without consciously following the recipe anymore. This is the same thing. This is a 4-step recipe. I'm asking you to follow it to the letter until you become really good at it. And then you still got to do the steps, but it doesn't have to be quite so formal anymore once you become really good at it, like once you become really good at making cinnamon buns. First step is draw a Freebody diagram. Draw a Freebody diagram. Show all of the forces that act on the object. In the second step, I want you to set F net equal to the sum of all of the forces. F1 plus F2 plus, I don't know, maybe you only have one force. In that case, F net is equal to F1. Maybe you have 14 forces. So F net is equal to F1 plus F2 plus all the way up through F14. F net is equal to all of the forces that you have added together. Then I want you to set F net equal to M times A. So in other words, these two steps combined are going to go from F net is equal to F1 plus F2, F net is equal to M times A. It's going to go to this. MA is equal to F1 plus F2 plus however many forces I have. See what I've done there? F net is this. F net is this. So this has got to be equal to this. And now, that comes the easy part, usually. Sub in your numbers. Solve something. Don't worry about what you're looking for. It'll fall out. It'll come out of it. Just sub in your numbers and get whatever you can get. What you're looking for will come out of this. Don't forget your directions, though. If F1 is to the right and F2 is to the left, make sure you make F2 a negative value. Not in the equation, but when you sub in the number. The best way to illustrate this is with an example. We'll follow the steps explicitly in this example. When I assign problems, after I do that example, I want you to explicitly follow the steps. And then, once you become really good at it, you can maybe you can combine step 2 and 3, little stuff like that. Okay, but for the time being, do the steps 1, 2, 3, 4 very explicitly. In fact, we're going to actually label the steps as we go. This question says, a 20-kilogram wagon is pulled to the right by one person with a force of 200 newtons, and it's pulled to the left by another person with a force of 120. There's a force of friction that acts against the wagon. What's the wagon's acceleration? Step 1, and I'm going to explicitly label that as step 1, draw a Freebody diagram. Here's the wagon. It doesn't have to look like a wagon. It doesn't have to have wheels. It doesn't matter what it looks like. It's an object. It's a 20-kilogram wagon. It's a 20-kilogram rock. Who cares? Same thing. There is a force of gravity acting down on that wagon. There's also a normal force acting up on the wagon. And that normal force is equal and opposite to the force of gravity. If it wasn't, well, then it would either accelerate up or down. But typically, wagons don't. Now, I could have drawn the normal force right here. I didn't, but I could have. It doesn't matter where you draw each of the forces, as long as you draw them in the right direction and roughly the right length. I just drew them right beside each other because that's the tidiest place to draw it for this diagram. Now we have a force to the right. I'm going to call that F1. It's 200 newtons. You could call it FR for force to the right. You could call it FA, representing your first force. You call it whatever you want. I'm calling it F1. I have a force to the left of 120. Make sure that you draw that F2, that 120 force, smaller than the 200, because 120 is smaller than 200. Now we have a force of friction as well. Which way is it going to act? Not both ways, no? Dylan? No, I thought you were raising your hand up there. Yeah, go ahead. No? Against which F? Yes, yeah. 200 is bigger than 120, right? So in the absence of friction, it will move to the right. If it moves to the right, friction is going to act to the left. Friction has to oppose the motion, right? Friction doesn't help you. Friction opposes the motion. So if you're moving to the right, friction is going to act to the left. I'm going to draw that as a really short force because it's much smaller than F2 and F1. It might not be to a perfect scale here, but it's showing us at least that FF is smaller than F2, which in turn is smaller than F1. Okay, that's step one. Step two. By the way, step one, I'm just going to cross those off. How come? Because what? It's not extraneous per se, but they balance each other, right? When I'm standing on the ground, the normal force is the same as gravity, so they balance. So why bother including them if they just cancel it anyways? So I'm going to say F net is equal to the sum of the forces, at least the sum of the forces that are left. F2 plus FF plus F1. How did I know to put them in that order? Well, yes, but it's a bit of a trick question. Yeah. Well, that's the order that they're in there. We don't have to put them in that order. It doesn't matter whether it's F2 plus FF plus F1 or FF plus F1 plus F2. It makes no difference. Put them whatever order is convenient for you. That's step two. Now, step three is to replace F net with M times A. F2 plus FF plus F1. Mass, step four is sub in your numbers. The mass is 20 kilograms. A is what I'm looking for. F2 is 120 newtons. FF is 15 newtons. F1 is 200 newtons. Right? Right, Megan, is that right? Almost. What's not right about it? What am I missing there? No. Yeah, we've got to find acceleration, but Karen? Yes, the 120 and the 15 are negatives because they're to the left. So we're going to say 20 times A is equal to 200 minus 120 minus 15 gives me 65. So A ends up being 65 over 20, which is 3.25 or 3.3 meters per second squared. Or you could have said 3.3 newtons per kilogram. Which way does it accelerate, left or right? To the right. How do you know? Yeah, it's two ways you can tell. One, that we get a positive acceleration. The second way is that we have a force bigger to the right than we do to the left. Make sense? All right, here's what I want you to work on for the remainder of class and for homework tonight. In addition to your quiz tomorrow on inertia, mass, force, all those definitions, the three things that a force can do, Newton's first law, okay, those Newton's second law problems. In addition to that quiz, I want you to work on worksheet number 11, questions 1 to 6.